Good evening, everyone. In today's lecture, we are going to start revision for mole concept and stoichiometry. It is one of the most important chapter of the chemistry, since everywhere now onward in every chapter you will use the concept of mole. In this particularly today's lecture, we are going to do some basic calculations related to mole calculations or mole concepts. So let's start from definitions of the moles. I will tell you some basic information related to moles and its calculations, and we'll do many numericals based on this. So let's say first we'll start from definition of the mole only. So as per mole concept is concerned, as per let's say mole concept is concerned. So first we'll define the term mole only. Here if you see the meaning of let's say 1 dozen. So 1 dozen you can say it is 12. A 12 identity you can say either 1 dozen of apple means let's say it is 12 apple. You can say 1 dozen of banana is nothing but let's say 12 banana. Similar to this, if we have, let's say 100, you can say it is 1 into 10 to the power 2. Similarly, if we have, let's say 1 million, it is nothing but 1 into 10 to the power 6. And if you think, let's say big enough, here you can say, let's say 1 mole. 1 mole is 6.022 into 10 to the power 23. So it is actually the huge number. It is also known as Avogadro's number, and it can be represented by either you can say it is represented by NA, it may be represented by N naught, or simply it can be represented by capital N. So here if you see basically as per mole is concerned, mole is basic unit of counting. It is basic unit of counting and should be used for microscopic particles only, and should be used for microscopic particles only. Now just try to imagine how big is a mole. So mole is actually the huge number. So if you just try to see some comparison, some analog here, 1 mole of marble would cover entire earth, including ocean, for a depth of 3 mile height. So you can just try to imagine, 1 mole of let's say $100 bills stacked one on top of another would reach from sun to Pluto and back 7.5 million times. It would take light 9500 years to travel from bottom to top of the stack of 1 mole of $1 bill. So actually, if you see, the mole is actually the huge number. It should not be used for counting of macroscopic object. For example, you can't imagine 1 mole of apple, 1 mole of bananas, 1 mole of let's say any macroscopic object. But obviously, If you just try to imagine 1 mole of electron, proton, neutron, something like this, then it is feasible. So if you see the meaning of 1 mole of, let's say, sodium atoms. So the meaning of 1 mole of sodium atom is 6.022 into 10 to the power 23, let's say, sodium atoms, and it is same as Na, or simply you can say Avogadro number. Na times of sodium atom. Similarly, if we have, let's say, 1.5 moles, let's say anything, 1.5 moles of O2 molecules, so it can be written as 1.5 multiplied by 6.022 into 10 to the power 23 O2 molecules, and it may be further equal to 1.5 Na of O2 molecules. Now, similarly, something if it is written as 1, let's say, small m, 1 m moles, so it is something very similar to millimeter or milligram. 1 m mole is, let's say, 1 millimole. 1 millimole of, you can say it is nitrate ion. So 1 millimole, milli means, some, for example, milligram is 1 upon 1000 gram. Millimeter is, let's say, 1 upon 1000. So if you see milli means 1 by 1000 times. So it is, let's say, 1 divided by 1000 into 6.022 into 10 raised to the power 23 of, let's say, nitrate ions, and should be equal to Na divided by 1000 of, nitrate ions. So as per 1 mole is concerned, it is just a counting unit, can be used for, let's say, microscopic particle, including sodium, oxygen, including atoms, including molecules, ions, electrons, neutrons, anything. Now, see the basic significance. If you see the basic significance of mole, you can just try to imagine, let's say, mass. So mass of 1 atom. Mass of 1 atom of 1 H1 should be equal to, you can say it is 1 AMU. If you remember, 1 AMU means it is approximately 1.67 into 10 to the power minus 24 grams. So it is the mass of, let's say, 1 atom of 1 H1. Simple isotope of hydrogen. Similarly, let's say if you have to find out the mass of 1 mole of 1 H1 atom, it should be equal to, let's say, it should be equal to 1.67 into 10 to the power minus 24 multiplied by 6.022 into 10 to the power 23 grams. So if you know the mass of 1 atom, it is just to multiplied by Avogadro number to find out the mass of 1 mole of atom. You will be surprised to know this comes out to be precisely 1 gram if you take exact value of AMU and exact value of Avogadro number. So if you see, these two numbers are found to be reciprocal of each other. Their multiplication is found to be 1. And if you remember, gram atomic mass of hydrogen is also found to be same as 1 gram. So gram atomic mass means it is atomic mass expressed in gram. I hope these things you can remember easily. So it is atomic mass expressed in gram. So gram atomic mass of hydrogen is, let's say, 1 gram. Atomic mass expressed in gram is gram atomic mass and comes out to be, let's say, 1 gram. So if you see basic comparison here, it is also 1 gram. It is same amount. It is 1 gram. So simply you can say mass of 1 mole of hydrogen atom is same as its gram atomic mass. Mass of 1 mole of hydrogen atom is same as its gram atomic mass. So point is, instead of, let's say, hydrogen, you can just try to imagine some another atom, another element also. So instead of hydrogen, if you take here, let's say, carbon 612, which is the basic standard unit, the mass of one atom of carbon 12 is found to be 12 AMU, and it is 12 multiplied by 1.67 into 10 to the power, let's say, minus 24 gram. Here, mass of, 1 mole of 6C12 atom, mass of 1 mole of 6C12 atom should be equal to, it is 12 multiplied by 6.022 into 10 to the power 23 multiplied by 1.67 into 10 to the power minus 24 gram, and comes out to be 12 gram. Gram atomic mass of carbon, it is also found to be, 12 gram. We know atomic mass of carbon is 12, so gram atomic mass comes out to be 12 gram. So same logic, if you see the mass of 1 mole of, carbon, 1 mole of carbon atom is same as its gram atomic mass. So you can generalize this concept for every element, for every atom. As we have seen for hydrogen and carbon, it is similarly applicable for any other element, including sodium, potassium, rubidium, anything. So if you see few points which you can remember related to atomic mass, related to molecular mass, calculations of number of moles. So the first point you can remember it as the same thing we have just seen, gram atomic mass. Gram atomic mass of any element. Gram atomic mass of any element is same as mass of its 1 mole. The mass of its 1 mole of atoms. Such that in given amount, let's say जो amount है, it is given in grams, such that in given amount, let's say this amount is given in grams mass, number of moles of atoms should be equal to. So according to unitary method, it is amount given in grams divided by, let's say, the mass of 1 mole of atom, which is gram atomic mass. So I'm repeating again, as gram atomic mass was the mass of 1 mole of atom. So if you have to find out the number of moles, it is amount given should be divided by mass of 1 mole of atom. It will be number of moles. For example, in 46 gram of sodium, in 46 gram of sodium, which is nothing but, let's say, Na1123 as a sodium, its atomic mass or gram atomic mass is found to be, let's say, same as 23 gram. So in this case, moles of sodium atoms should be equal to 46 gram is given as the mass divided by, let's say, 23 gram, and it comes out to be 2 moles of sodium atom. It means if we have to find out, let's say, number of sodium atoms, it is nothing but, let's say, 2 moles. It may be written as 2Na. It may be equal to twice of 6.022 into 10 to the power 23, which is eventually comes out to be 1.2044 into 10 to the power 24. So as per gram atomic mass of any element is concerned, it is the mass of 1 mole of atom, such that in given amount, which is given in grams, if you have to find out the number of moles, it is amount given, obviously, in the unit of grams divided by gram atomic mass, which is the mass of 1 mole of atom. So in 46 gram of sodium, for example, sodium is 1123. 11 is number of proton, 23 is mass number. Moles of sodium atom should be 46 gram divided by 23 gram, comes out to be 2. 2 moles means it is twice of Na, and it is nothing but, let's say, twice of 6.022 into 10 to the power 23, which is eventually comes out to be 1.2044 into 10 to the power 24. So the same thing we can see for molecules also. So if you see, let's say, point 2, the second point you can remember. Gram molecular mass, similar to gram atomic mass, which is defined for element. Gram molecular mass can be defined for, let's say, compound. So gram molecular mass of any compound, gram molecular mass of any compound is mass of 1 mole. Gram molecular mass of any compound is mass of 1 mole of molecules such that in given amount, with the amount may be given in grams, moles of molecules should be equal to, is again, let's say, amount given in the unit of grams divided by amount given in the unit of grams divided by, let's say, gram molecular mass. It is something very similar to that of whatever we have done in point 1 related to elements. It is for compounds now. For example, if we have, let's say, 54 gram of water, so the molecular mass of water is found to be 18. Oxygen atomic mass is 16 and 1 each from hydrogen. So its molecular mass is 18 and its gram molecular mass is 18 gram. So in 54 gram, if we have to find out, moles moles of water molecule. If we have to find out, let's say, moles of water molecule, it should be equal to amount given again in the unit of, let's say, grams divided by, let's say, molecular mass. So you can directly write the figures only. It is 54 gram and it will be nothing but 18 gram and it should be 3. So in 54 gram of H2O, the moles of water molecule is 54 gram divided by 18 gram and it comes out to be, let's say, 3. If we have to find out number, let's say, number of molecules, it should be nothing but, let's say, 3 Na. And it is nothing but, let's say, 3 Na, or you can simply say 3 moles, or it is thrice of 6.022 into 10 to the power 23. So these many water molecules, this is actually again the huge number present in 54 gram of water. So as per atoms or molecules are concerned, they are very, very, very small, very small piece of any matter. I hope now you understand how we can find out the number of moles of atoms or number of moles of molecule in a given amount. So we can see a few more points to remember. Let's say third point is although atomic mass is just a ratio of, if you say atomic, just a ratio of atomic mass of, given element to, if you remember its definition, it is 1/12 mass of carbon 612 atoms. There was the definition of, atomic mass, and thus it should not have any unit. I'm repeating again, although जो atomic mass है वो बस एक ratio है and it should not have any unit, but sometimes it can be expressed by some units also. For example, let's say atomic mass. Atomic mass of sodium, you can say it is 23. It may be written as 23 AMU, and let's say it is per atom of sodium, and it is nothing but, let's say, 23 gram per mole of atoms. So it is as simple, again, the same correlation. Gram atomic mass of any element is the mass of its 1 mole of atoms. So whenever, suppose if it is written as atomic mass, if anywhere it is written as atomic mass of oxygen is, let's say, 16, and if it is written as 16 AMU, then you can simply imagine it is the mass of its one atom. If it is written as, let's say, 16 grams, so confirmly it is the mass of its 1 mole of atoms. So whatever, let's say, mass is given, let's say, for example, it is 16 given. So it may be given in terms of, let's say, AMU means it is the mass of one atom. And if it is given as, let's say, 16 gram, it can be the mass of, let's say, 1 mole of atoms. Same, let's say, fourth point you can remember is volume. Volume occupied by 1 mole of, gaseous molecules. Volume occupied by 1 mole of gaseous molecules at, it is NTP. Or let's say you can say it is STP also, or NTP means it is normal temperature and pressure. NTP, normal temperature and pressure, which is 0 degrees Celsius and 1 atmospheric pressure. Volume occupied by 1 mole of gaseous molecule at NTP. NTP means it is normal temperature and pressure, which is 0 degrees Celsius and 1 atmospheric pressure, is 22.4 liter. So you have to remember this statement. We'll derive this statement, we'll derive this relation in another chapter known as gaseous state of matter. But as per mole concept is concerned, you have to remember this. So volume occupied by 1 mole of gaseous molecule at NTP, which is normal temperature and pressure, or which is, you can say, 0 degrees Celsius and 1 atmosphere. 1 atmosphere is the pressure unit, is 22.4 liter. For example, volume occupied by, if you see, let's say volume occupied by 22 gram of CO2. 22 gram of CO2, obviously gaseous molecules. So first you have to find out how many moles of CO2 molecule present in 22 gram. So first thing is, let's say, number of moles. Number of moles, it should be 22 divided by, let's say, gram molecular mass of CO2, which comes out to be 44. And once it comes out to be, let's say, half mole of molecules, then volume. Volume occupied at NTP. Volume occupied at NTP is half, and it is 22.4 liter per mole. So it comes out to be 11.2 liter at NTP. So the point is, if it is a mass given, you have to convert the mass into moles first, and then moles has to be multiplied by 22.4 liter, which is volume occupied by 1 mole, comes out to be 11.2 liter. I hope you have noted down all these, these 4 points. I'm repeating again. The first point related to calculations of mole was gram atomic mass of any element is same as mass of its 1 mole of atoms, such that given amount may you have calculated the number of moles of atoms. Similarly, if we see for any compounds, gram molecular mass of any compound is the mass of 1 mole of molecule. So moles of molecule is amount given in grams divided by gram molecular mass. Same, let's say next one. Although atomic mass is just a ratio of atomic mass of any element to 1/12 mass of 6C12 atom, and thus it should not have any unit, but sometime it can be expressed by some units also. For example, if it is given, if the mass is given in terms of AMU, confirmed it is the mass of one atom. And if mass is given in grams, it is the mass of 1 mole of atoms. Let's say. Same, the last point we have discussed now. It is the volume occupied by 1 mole of gaseous molecule at NTP. NTP means it is normal temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, is 22.4 liter. Volume occupied by 22.4, 22 gram of CO2 molecule. If we have to do this type of question, you have to convert mass into moles first. For example, number of moles has to be mass given divided by gram molecular mass of CO2, which is 44, comes out to be half moles, and volume occupied at NTP, normal temperature and pressure, is half mole multiplied by volume occupied by 1 mole, comes out to be 11.2 liter. Now to summarize all these 4 points, so you can need, let's say, another point, let's say 5 here. So 5 is related to interconversion in moles calculation. So, it is interconversion. The meaning of interconversion, let's say here, you can just try to imagine this may be, let's say, some cloud type of thing. This may be, let's say, another one. And let's say this may be another one. So somewhere in middle, we have, let's say, number of moles. Number of moles. Somewhere here, it is amount given. Obviously, amount given has to be in the unit of grams. It is related to number of particles. It is related to, let's say, number of particles, number of atoms, number of molecules, something like this. And it is volume. It is volume occupied. It is volume occupied at NTP. It is a volume occupied by NTP by, gas molecules. It is volume occupied at NTP by gaseous molecules. So if you have to interconvert them, so whenever number of particles are given and you have to find out, let's say, number of moles, it has to be, divided by Avogadro number. And same from number of moles, if you have to find out number of particles, it has to be, multiplied. It has to be multiplied by Avogadro number. Similarly, from number of moles, if we have to find out, let's say, the amount, so this need to be multiplied by gram atomic mass, or let's say gram molecular mass, and let's say it is divided by gram atomic mass, or divided by gram molecular mass. It is as simple. If we have to find out volume occupied at NTP by gaseous molecule, so this need to be multiplied by, let's say, multiplied by 22.4 liter. And obviously from here you can say it has to be divided by 22.4 liter. So if you see the interconversions, number of particles divided by Avogadro number to find out number of moles, and number of moles need to be multiplied by Avogadro number to have number of particles. Number of moles can be multiplied by gram atomic mass or gram molecular mass, and amount given should be divided by gram atomic mass or molecular mass to find out, let's say, number of moles. Number of moles can be multiplied by, let's say, 22.4 liter to find out volume occupied at NTP. And similarly, to comes back, you have to just see this arrow ka direction. Need to change this arrow direction. If we have volume already and we have to find out number of moles, it has to be divided by 22.4 liter. Now, one by one, we'll do many questions based on this, whatever we have done till now, related to theory, related to moles calculations. I will solve around 9 to 10 questions for you, such that you will get basic idea related to how to calculate. So first questions related to this is, if you know mass of one atom, if you know mass of one atom of given element is, suppose it is given as 6.626 into, 10 to the power minus 23 gram, then find out its atomic mass. If mass of one atom of given element is 6.626 into multiplied by 10 to the power minus 23 gram, and if you have to find out its atomic mass. So let's say here we have two methods to find out its atomic mass. Method one is, you can say, it is by definition of atomic mass. So by definition of atomic mass, so as per definition of atomic mass is concerned, atomic mass should be equal to the ratio of, you can say, mass of one atom of given element to 1/12 mass of 6C12 atom. Atomic mass should be equal to mass of one atom of given element to 1/12 mass of 6C12 atom. And as per calculation is concerned, it is 6.626 into 10 raised to the power minus 23 gram divided by, it is 1/12 mass of 6C12 atom should be equal to, let's say, 1/12 of 12 AMU. 12 AMU means 12 multiplied by 1.67 into 10 to the power minus 24. So it is given in the unit of grams, and grams should be equal to. So obviously this 12 and 12 will cancel it out. So it is effectively 6.626 into 10 to the power minus 23 divided by this, and comes out to be approximately 40. So you can simply say 40 should be atomic mass of given element. So this is the method 1. As per method 2 is concerned, so you can say y, let's say 0.1. The 0.1, the point to remember we have seen. So 0.1 was, gram atomic mass is mass of 1 mole. Gram atomic mass is same as mass of 1 mole of atoms. And in this case, let's say gram atomic mass, which is the mass of 1 mole of atom, should be equal to 6.626 into 10 to the power minus 23 gram, need to be multiplied by Avogadro number, which is 6.022 into 10 to the power 23, and it also comes out to be approximately 40. So either you follow, let's say, method 1 or method 2. This is the question related to if mass of 1 atom of given element is given, and you have to find out the mass of, let's say, 1 mole of atom, which is same as, let's say, atomic mass. I hope both methods are clear to you. One is atomic mass, and let's say, one is by definition of atomic mass. And another thing is the point you have written just now related to 5 points you have note down related to calculations of mass, and this according to, let's say, first point only. So another question related to this is, what's the question number 2? Let's say you have to find out, following in 54, or simply you can say, let's say, 36. In 36 gram of water. You have to find out following in 36 gram of water. The first thing you can say, A part is number of water molecules. The first point is, let's say, number of water molecules. B part is, let's say, number of hydrogen atoms. C part is, let's say, number of oxygen atoms. D part is total number of atoms. E part is, number of protons. It is number of neutrons. It is number of electrons. Let's say it is mass of oxygen. And if we have to find out mass of hydrogen. So you can take some time to calculate this. You have to find out, let's say, number of water molecules. You have to find out number of hydrogen atoms, number of oxygen atoms, total number of atoms. You can find out number of protons, neutrons, electrons. You can find out, let's say, mass of oxygen out of 36 gram of water, and the mass of hydrogen out of, let's say, 36 gram of water. So you have to use, let's say, few points which we have just noted down related to 0.1, 0.2 up to 0.5. So, gram molecular mass. If you see the basic calculations, gram molecular mass of water comes out to be 36 gram. Gram molecular mass of water comes out to be, let's say, same as, let's say, 36 gram. Oh, it is 18. Gram molecular mass of water comes out to be 18 gram, out of which, confirmly, you can say, as per H2O is concerned, it consists 1 H1 and it consists oxygen 16. So we have 2 atoms of hydrogen per molecule and obviously 1 atom of oxygen. So gram molecular mass of water is 18 grams. So you can say 18 gram per mole. And this number of water molecule according to point 2 is 36 gram divided by mass of 1 mole of atom, and thus it should be 2 mole. So as per answer is concerned, you can say it is 2 moles, or you can say it is 2Na. Number of water molecules should be equal to, let's say, 2 moles or 2Na. Here number of hydrogen atoms is concerned. Confirmly, number of hydrogen atoms should be, let's say, 4Na, as every water molecule consists 2 hydrogen atom. Number of oxygen atoms should be equal to, let's say, 2Na, and total number of atoms, you can just add oxygen atom and hydrogen atom. It should be 6 times of Avogadro number, 6Na, which is number of total atoms. Number of proton, as every water molecule consists 10 protons, and you can say it should consist 10 electrons, and it should consist only 8 neutrons, as hydrogen atom does not consist any neutron. So it is 10 proton, 10 electron, and let's say 8 neutrons. As per number of protons are concerned, as per number of protons are concerned, every water molecule consists 10 protons, so 10 proton multiplied by 2Na, it comes out to be, let's say, 20Na. Number of neutron should be nothing but, let's say, 18Na. Number of electron should be nothing but, let's say, 20Na. Mass of oxygen. Now, total mass is 36 gram. Out of this, as in 18 gram, water mass is found to be 16 gram, and hydrogen mass comes out to be 2 gram. So if you see, as per water molecule is concerned, in water molecule, hydrogen mass is nothing but, let's say, 2 gram. Oxygen mass comes out to be, let's say, 16 gram out of total, let's say, 18 gram. So mass of oxygen comes out to be, 32 gram, and the mass of hydrogen, the remaining mass out of 36, it comes out to be 4 gram. So I'm repeating again. As per water molecule is concerned, its gram molecular mass comes out to be 18 gram per mole. It means for 1 mole of water molecule, the mass is found to be 18 gram. Number of proton, it is 10 proton, 10 electron, and 8 neutrons are there per water molecules. In 36 gram of water, we have 2 moles of water. It is nothing but twice of Na as per number of molecules are concerned. Number of hydrogen atom comes out to be 4 Na. It should be twice of number of water molecule. Number of oxygen atom is same as number of water molecule. Total number of atoms, you need to add hydrogen atoms and oxygen atoms. Number of protons. Every water molecule consists 10 protons. So 2 mole means 2 mole multiplied by 10. It should be nothing but 20 moles. 20 moles means 20 times of Avogadro number. Number of neutron, which is nothing but 18 moles. So basic definition, basic difference between number of proton and number of neutron is hydrogen atoms. Hydrogen atom consists 1 proton, 1 electron, but it does not consist any neutron. So neutron contributed only from, let's say, oxygen, and that's why we do some mistake here. As per number of neutron is concerned, it should be nothing but 16 Na. You just make a correction in point F. Number of neutron should be nothing but 16 Na, as number of neutrons comes from oxygen only. There is no neutron in hydrogen. So you have to just make this correction here. As per number of electrons are concerned, again it is same as number of proton. The mass of oxygen, as oxygen was 16 gram out of 18 grams, so it comes out to be total as 32 gram out of 36 gram. Mass of hydrogen is remaining mass, which is 4 gram. I hope now this question is clear to you. So should move to the next one. So question number 3. It's very common questions in previous year, JEE Main, many engineering competitive exams, medical exams. Find out mass, or find out percentage. Find out percentage of nitrogen in urea. So urea is one of the most common versatile fertilizer used by farmers in India. So you have to find out percentage nitrogen in urea. So to do this question, we need to know the molecular formula of urea. So as per urea is concerned, its molecular structure may be represented as CO and let's say bonded with NH2, or it is nothing but CO NH2 whole twice. As per urea molecular formula is concerned, urea is nothing but let's say CO NH2 whole twice, and this is the overall molecular formula, CO NH2 whole twice. In this case, molecular mass. In this case, molecular mass comes out to be 60. 60, it is how come? Carbon 12, oxygen 16, nitrogen 28, and 4 from hydrogen. So its molecular mass comes out to be 60 in total. Out of 60, if you see the mass of nitrogen, so if you see percentage nitrogen should be equal to, mass of nitrogen divided by total mass multiplied by 100. So mass of the nitrogen comes out to be, let's say, 28, as we have 2 nitrogen and 2. 28 out of total mass, which comes out to be 60 into 100, and it comes out to be 46.67%. So it comes out to be 46.6666 and so on. So it is nothing but, let's say, percentage nitrogen. So it is the mass of nitrogen divided by total mass into 100. I hope it is clear. So if nothing is mentioned related to percentage, it is always percentage by mass. I'm repeating again, if nothing is mentioned related to percentage, it is always percentage by mass. So first we have find out, let's say, the total mass of nitrogen, and total mass of nitrogen divided by, total mass of the molecule into 100 will be nothing but, let's say, the percentage nitrogen here. So next question, let's say question number 4. And in question number 4, let's say find out mass. Find out mass of oxygen correspond to, 6.2 gram of phosphorus in a sample of, calcium phosphate. You have to find out the mass of oxygen correspond to 6.2 gram of phosphorus in a sample of calcium phosphate. So calcium phosphate is nothing but, let's say, Ca3PO4 whole twice. Calcium phosphate. So as per answer is concerned, for answer you should know the atomic mass of oxygen, you should know the atomic mass of phosphorus. So it is given, let's say, in the question only. Atomic mass of phosphorus is found to be 31, and for oxygen it is found to be 16, as per atomic mass is concerned. So as per answer of given question is concerned, as per, let's say, calcium phosphate, as per calcium phosphate is concerned, with 31 gram of phosphorus, which is the atomic mass of the phosphorus, we have 4 multiplied by 16 comes out to be 64 gram of oxygen. So with 31 gram of phosphorus you have 64 gram of oxygen. So again you can apply unitary method. For 6.2 gram of phosphorus, how much mass of oxygen is there? So you can say, let's say, mass of oxygen. Mass of oxygen should be equal to, mass of oxygen should be equal to, it is 64 when phosphorus ka mass is 31, and this need to be multiplied by 6.2. So you can simply say this 31 multiplied by, let's say, 6.2 is nothing but, let's say, 0.2, and 0.2 multiplied by, let's say, 64 comes out to be, let's say, 12.8 gram. So in a sample of, let's say, calcium phosphate, I'm repeating again, in the sample of calcium phosphate correspond to 6.2 gram of phosphorus. It is 12.8 gram of oxygen is there. And again, to calculate this, we know the molecular formula of calcium phosphate. Per phosphorus atom, we have 4 oxygen atom technically. So 31 gram is the gram atomic mass of phosphorus, and 16 gram is the gram atomic mass of oxygen. So it is 31 gram. Correspondingly, oxygen mass is nothing but, let's say, 64 gram. I hope it's clear. Next question. Let's say question number 5. Find out, let's say, mass of water which consists. You have to find out, let's say, the mass of water which consists same number of hydrogen atoms. Find out mass of water which consists same number of hydrogen atoms as present in. Find out the mass of water which consists same number of hydrogen atoms as present in, 12 gram of urea. So find out mass of water which consists same number of hydrogen atoms as present in 12 gram of urea. So here, let's say we have water, and simply you can say, let's say here we have urea. From here, you can imagine, let's say if we have X gram of water and urea ka mass, which is already given as 12 gram. Urea molecular formula, we already know it is CO, carbon, oxygen, and it is NH2 whole twice. And its molar mass also comes out to be 60. The 60 you can easily find out. It is carbon is 12 atomic mass, oxygen atomic mass is 16. For nitrogen, it should be 14 into 2, and for hydrogen, it is 1 into 4. So for water, it is, let's say, X gram. For urea, it is given as, let's say, 12 gram. As per number of hydrogen atoms are concerned. As per number of hydrogen atoms are concerned, it is X divided by 18. In water, it is number of water molecules. If it is multiplied by 2 times of Na, or first you can just say it is X divided by 18, which is mass divided by gram molecular mass of water, is the moles of water molecule multiplied by Na will be the number of molecules, and number of molecules multiplied by 2 will be the number of hydrogen atoms. So these are the number of hydrogen atoms here. Should be equal to, it is 12 gram divided by 60. Mass divided by molecular mass. Mass divided by molecular mass is nothing but, let's say, number of moles. Number of moles of urea multiplied by Na, ये हो जाता number of, let's say, urea molecules. Number of urea molecules multiplied by 4 will be number of hydrogen atoms. And both water as well as urea, they should consist same number of hydrogen atoms, in which Na and Na is cancelled out. This comes out to be, let's say, 2 here. This comes out to be, let's say, 5. And thus, as per, let's say, X is concerned, it should be 36 divided by 5 and comes out to be 7.2 gram. So I'm repeating again the same solution. For water, you can imagine it is, let's say, X gram. For urea, you can imagine, let's say it is 12 gram, which is given in the question. As per urea is concerned, its molecular mass is 60. For water, molecular mass is 18. So first we have find out number of water molecule. For example, as per this bracket is concerned, it is nothing but number of water molecules. And as per this bracket is concerned, it is nothing but number of urea molecules. One is number of water molecule, another is number of urea molecules. So X should be equal to 36 by 5, comes out to be 7.2 grams. So we need more questions to do. So next question is, let's say question number 6. Find out volume occupied. Find out volume occupied by following at NTP. You have to find out volume occupied by following at NTP, which is normal temperature and pressure. The first one is, let's say if we have 11 gram of, CO2 molecule. So we can do one by one, let's say. If we have 11 gram of CO2 molecule, now if you see the interconversion, grams has to be converted into moles first, and moles multiplied by 22.4 will be the volume occupied at NTP. As per 11 gram is concerned, you can say volume occupied. If you see volume occupied is 11 divided by 44 gram molecular mass is number of moles. Number of moles multiplied by, let's say, volume per mole, which is 22.4 liter, comes out to be, let's say, 5.6 liter. So 11 gram of CO2 molecule. So volume occupied should be equal to 11 divided by its molecular mass multiplied by 22.4 liter, comes out to be, let's say, 5.6 liter. Similarly, second one. Suppose if we have to find out volume occupied by, 1.5 moles of O2 molecules. If we have to find out volume occupied by 1.5 moles of O2 molecules, in this case, volume occupied. In this case, volume occupied should be equal to, it is 1.5 multiplied by, 1.5 multiplied by 22.4 liter, which is same as 22.4 liter is volume occupied by 1 mole. So 1.5 into 22.4 comes out to be 33.6 liter. So it is the volume occupied by, oxygen gas, 33.6 liter. Same. Let's say if it is given as 1 moles of water molecule. 1 moles of water molecule. Then if you have to find out volume occupied. Volume occupied at NTP. So there is a catch in third part. The volume occupied at NTP or STP is 22.4 liter for 1 mole of gaseous molecule. So just remember, as per water is concerned, at NTP, it is not a gas. It is not gas at NTP. So you can't say the volume is 22.4 liter per mole. You need to know density of water. Density of water is, we know it is 1 gram per milliliter. Density of water is nothing but, we know it is 1 gram per milliliter. And thus 1 mole. So again, I'm repeating here, as water is not gas at NTP, which is 0 degrees Celsius, 1 atmosphere, you can't apply 1 mole of water molecules can occupy 22.4 liter. So here it is 1 mole of water molecules. Volume occupied at NTP should be equal to, volume occupied by water molecules at NTP should be equal to, density is 1 gram per milliliter. And 1 mole of water is nothing but, let's say, 18 gram. So can we say volume occupied at NTP should be equal to, let's say, 18 milliliter. Volume occupied at NTP should be nothing but, let's say, 18 milliliter. I hope this question is also clear to you. Density, so you have to just remember the last one. Water is not gas at NTP, so you can't apply 22.4 liter per mole here. You have to do calculation according to, let's say, density, mass and volume ka ratio. Further, the next one more question we can do. Let's say question number 7. Arrange following into decreasing order. Arrange following into decreasing order of their number of atoms. Arrange following into decreasing order of their number of atoms. Let's say here, first one, it is given as 1.5 moles. 1.5 mole of S8, sulfur molecules. The second is, suppose it is given as 36 gram of water. Similarly, if it is given as, 33.6 liter of CH4 gas at NTP, and fourth, it is given as 1.2 Na of SO3 molecules. 1.2 Na of SO3 molecules. So one by one, we have to find out their number of atoms. One by one, you have to find out their number of atoms here. So in first one, 1.5 moles means 1.5 Na and multiplied by 8, let's say. S8 per molecule, we have 8 atoms, and 1.5 into 8. 1.5 into 8 is, let's say, 12. So it comes out to be 12 Na. It is the first part. Second part is 36 gram of water. So 36 gram of water means 36 divided by 18. Na will be number of water molecules, and every water molecule consists 3 atoms and should be equal to. It is 2 into 3. It comes out to be, let's say, 6 Na. This is for second, 36 gram of water. It is again, 33.6 liter of CH4. So it is 33.6 divided by 22.4 moles of, CH4 molecules. So these many moles multiplied by Avogadro number. These many molecules multiplied by 5 for CH4. So it comes out to be, let's say, 3 by 2. It is 15 by 2. Comes out to be 7.5 Na. It is technically 3 by 2 multiplied by 5. Same in the case of 1.2 Na of SO3 molecule. So 1.2 into Na, and SO3 means already it consists 4 atoms. It should be equal to. It comes out to be 4.8 Na. So if you see the arrangement of 1, 2, 3, 4 in decreasing order of their number of atoms. It is 1 has highest number of atoms, then it should be, let's say, 3, and then it should be, let's say, 2 as number of atoms is concerned, and then it is, let's say, 4 as number of atoms are concerned. So total number of atoms, it is 1, 3, 2, 4. I'm repeating the complete calculations once again. If you have to arrange following into decreasing order of their number of atoms, 1.5 mole of S8 molecule, it is 1.5 into 8, let's say, comes out to be 12 Na. 36 gram of water means 36 divided by 18 into 3 comes out to be 6 Na. 33.6 divided by 22.4 Na comes out to be 7.5 Na, and 1.2 Na into 4 comes out to be 4.8 Na. So 1 has maximum number of particles than 3. 3 has more number of particles than 2, and 2 has more number of particles than 4. So overall, in today's lecture, we have done a basic moles calculations, the definitions of mole, how we can find out the number of atoms, number of molecules. In the next lecture, we'll continue with revision of moles and stoichiometry. So now we'll do, from the next lecture, the calculations of moles, mass, volume, density related to chemical reactions also. So keep revising the concept related to moles and stoichiometry. And in the next week, we'll have again lecture related to chemistry, mole concept and stoichiometry. And we'll continue from here on. So that's all from my side for today.